Good morning, everyone. Thanks for waking up and for coming to my talk. I will be talking about two recent papers with the same group. It is collaboration between my group and Elias's group. So Puchin Wang is my student and Nikos is Elias's student. And both Puchin and Nikos are amazing. They're super smart. They did almost all the work on both these papers. So I just wanted to kind of give them a shout out. So the talk will be structured in two parts corresponding to two papers. The first one appeared in ICML last year. The second one was just posted to the archive 2 days ago, I think. Okay, so the plan for the talk is basically to go through these two sets of results. The talk will follow the same structure. So I'll start with some context and related work, then I'll state the main results, and then I'll say a few words about the main ideas. The main difference between the two parts is whether or not we know the activation or a link function. I'll tell you in a minute what that is, but for now, let's just get started. So my talk has the single neuron in its title, and there are different names people use for these problems. The first part, what I'll talk about sometimes, is also called generalized linear models. But the bottom line is that there is some link or activation function. It's a univariate function, things like ReLU, Swish, or GALU, but it corresponds to a high-dimensional problem because here we apply a linear transformation to a data point that corresponds to a model or parameter vector W, and this W is what we're trying to learn. Now, for the first part of the talk, I will assume that I know precisely which activation function I want to fit. The results will apply to all three of these. They will apply to a broader class of activations. For simplicity, I will present the results mainly for ReLU because it will be easier to explain the results. Now, in our setup, of course, this is a learning problem. So there are some data vectors that are labeled. And our model is such that we draw these labeled data vector label pairs from some unknown distribution D. But what we assume here is that there is no perfect model. So it could be the case that I'm trying to fit a ReLU, and actually ReLU is not the right model for my data at all. So what I'm interested in is finding the best fit function. Other way to look at it is that the labels correspond to some function, but then there is arbitrary or possibly adversarial noise. But importantly, it is not a zero mean noise. So this corresponds to what people would call agnostic model. Okay, so what does it mean to find the best fit function? It means to minimize the mean square error, which is just the mean difference between what our model predicts as a label and the true label squared. Now, here I say approximately minimize, and I'll make this specific, more specific in a bit. But if you have background in optimization, you would quickly notice that for all these activation functions, this is a non-convex optimization problem. In full generality, it's not an easy non-convex problem, and we cannot really solve it. So ideally, what we would like to do is just minimize this to some additive error epsilon, but as you'll see in a bit, that's not generally possible. Okay, so this is just a reminder of what we're talking about. And so what I want to be able to be competitive with is the minimum value of this mean squared error, which I will call opt. Okay, so let's see what is known about hardness or easiness of this problem. If we are not making any distributional assumptions, this problem is incredibly hard. It is known to be NP hard. even if you were interested in proper learning, meaning that you don't necessarily output a model from your target class, but it can be something else, this is known to require super polynomial time just to get multiplicative plus additive error. Okay? So I'm not talking about additive error, so this is both for constant times opt plus epsilon. Now, if you make distributional assumptions, and the first thing to try is to look at the Gaussian covariates. Gaussian is the nicest distribution we have, right? Well, it turns out that finding W that gets error opt plus epsilon without the multiplicative error, this also requires super polynomial time. Okay? So the bottom line is that if we have some target error epsilon, the best that we can hope to achieve is error some constant times opt plus epsilon. And we need to look at structured classes of distributions. So in other words, we need both distributional assumptions and we need the multiplicative error for computational tractability. Okay, so going back to the problem statement, what we are trying to do is we are given sample access now to a structured distribution. We are given an activation function sigma, error parameter epsilon, and the set radius w. So this is actually quite typical to look at a bounded set of possible weight vectors. What we are interested in is finding a vector w such that for an absolute constant c, we get error c times opt plus epsilon, where, just to remind you, opt is the minimum squared error, and this capital F is just mean squared error. Okay, any questions about the problem itself? No? Okay, so let me then state the main result. The main result, a little bit informally stated, is that under mild distributional assumptions, we can use a very simple algorithm, which is just a mini batch stochastic gradient descent. Needs to have a sufficiently large batch size, sufficiently small learning rate. And we apply that to a certain surrogate of the problem. I'll talk about it in a bit. This mini batch SGD is guaranteed to converge to a vector W such that we get this target error constant times opt plus epsilon, where this C is an absolute constant. Okay, and again, this is the best guarantee we can even hope for based on what I've just told you. The number of iterations that SGD makes is log 1 over epsilon. The total number of samples that the algorithm uses depends on the concentration of one-dimensional projections of the X marginals or covariates. In particular, if we have sub-exponential concentration, this scales with poly log 1 over epsilon, which is basically as good as you can hope for. But we can also handle heavy tails that are of degree larger than 4. In that case, we get 1 over epsilon to 2 over k. Because we look at k larger than 4, this is always going to be smaller than 1 over root epsilon. Okay, any questions about the results? That doesn't include assumptions, because I'll tell you that in the next slide. Okay, so let's see what the distributional assumptions are. There are two main assumptions that we make. And you can think about them as a margin-like assumption and as a concentration. The margin-like assumption basically bounds the minimum eigenvalue of your covariance when restricted to the direction of one of the solutions. Okay, so you look at the covariance, but you're restricting only to a direction where you have some non-trivial alignment with one of the solutions. Okay, and we say this is bounded below by some constant. And here both lambda and gamma are constants. The second assumption is just your standard concentration. And as I said, we can actually handle polynomial tails, but they should be lighter than 1 over t to the fourth. Okay, questions about assumptions? Well, the first thing you should ask is this mild? And the answer is yes. For the same type of a result, which would be constant times opt plus epsilon, this subsumes everything that was in the literature in terms of the distributions that were handled, but it also can handle some other distributions, even discrete distributions like discrete Gaussian and uniform on a -101 hypercube. Okay, so let me tell you a little bit more about these assumptions and how it compares to what was known before. So all of the prior work that obtained the same error guarantee, in fact, required 3 sets of assumptions. The first set of assumptions that they required is anti-concentration, which basically means that if you look at any one-dimensional projection of the covariates, it shouldn't be putting too much mass in any interval. And what an anti-concentration does, it rules out possibly lower dimensional data. In our case, this is replaced by this margin-like assumption, which can also be interpreted as anti-concentration, but only in the direction of a solution. Okay. The second set of assumptions in prior work is concentration. And in particular, prior work assumed at least sub-exponential concentration, which of course rules out possibly heavy tail distribution. And in our work, we also allow for polynomial tails. The third set of assumptions that it was needed in prior work is known as anti-anti-concentration. And what anti-anti-concentration does is it requires that if you take the distribution of covariates and you project it on any low-dimensional space, like usually 1 or 2-dimensional space, the probability density function has to be bounded below. Okay, yes?
How can it be bounded below?
On bounded sets, on small bounded sets. Yeah, very good question, thank you. Should be more careful in how I state things. But basically what this prevents is having any gaps in the distribution, and so it rules out discrete distributions. It's the main reason why prior work could not handle discrete distributions, and it's something that we completely remove. We don't need it in this work. Now, to tell you a little bit more about related work, there are 2 main lines of work. The first line of work is trying to directly minimize the non-convex objectives, and then the results are based on proving that stationary points are good enough under strong distributional assumptions. The other set of results is working with a convex surrogate. This is what we do, but just to clarify, the convex surrogate is only used in the algorithm. We do not really rely on minimizing the convex surrogate. It's more an artifact of the analysis because we directly bound the mean squared loss. Now, among these results, only 2 prior papers would get a constant times opt plus epsilon having an absolute constant, and none of them handled any non-monotone activations. And if you do apple-to-apple comparison, so looking at the same classes of activations and same classes as distributions, the dependence on 1 over epsilon that we get is at least as good. Okay, because the prior work would get either, I think only one of them got polylog 1 over epsilon, the other ones were poly 1 over epsilon. Okay. I'll now tell you a few things about the main ideas. Before I go there, let me just stop to ask if there are any questions. No? Okay. I mentioned that in prior work, there are two main approaches which consist in either either minimizing directly the original squared loss or minimizing a convex surrogate that has been used quite a bit in this literature on generalized linear models. There are different ways, really, to motivate it, but the most important part is how the gradient of this behaves, and it is related also to something called Chow parameters, but I won't go into that in this talk. So what are some kind of pros and cons of using either of these two? Well, the original squared loss is what we are trying to minimize. So if you minimize it, you got the solution, so that's great, but it is non-convex even for ReLU, which is our most basic activation. And of course, for non-convex problems, we know how to find stationary points. But for this specific problem, the stationary point is not guaranteed to be a minimizer or achieve this constant times opt plus epsilon error. So you cannot get that for free. The thing about convex surrogate that is nice is that it is convex for all monotone activations. And we like working with convex functions because we know how to minimize them. If we get a stationary point for this, we know it's a minimizer by convexity, but the minimizer itself may not be the solution to the original problem. Okay?
So you don't work only with monotone activation.
I'm sorry?
You deal also with non-monotone.
We deal with some non-monotone activations, but we do need some assumptions about them. We cannot handle all non-monotone activations. We can handle things like ReLU and swish. I'll say just a few words about it when I show you just some of the ideas in the analysis.
So if sigma is a sine of t, sigma of t is sine of t, you cannot do it.
If it is just the sine, no. Okay. So the results that we obtain, we get by proving a structural property of the convex surrogate. And this structural property in optimization is called local error bound. There is prior work that called this restricted secant inequality, if you're interested in names. We call it sharpness. Sharpness is defined a little bit differently. Usually you have optimality gap here being bounded below, but there's a reason why we call it that, because we can also translate it into sharpness for the original squared loss. In case anyone is wondering about misnomers, I had that in one of the talks. So what local error bounds are, they are talking about local growth of the function. So in optimization for many problems, you can prove that if you step outside of the set of the optima, the function is going to grow reasonably well. Very often is going to grow as a quadratic function. Now, what that allows you to do, if you know about optimization, you usually need some type of a growth condition to actually have convergence in the vector itself, the convergence in solutions. It can be shown that some type of local error bound is going to hold for all reasonable problems. But the issue is that the constant that appears here can be trivially small. So in that sense, local error bounds are not always useful. But what turns out to be the case here is that under our assumptions, we can show that a local error bound holds with an absolute constant. That's going to depend on the constants that define our distributional assumptions, but it's actually not unreasonable to assume that those are constants. Okay, it is local. It only holds on some set, but I said there exists a set, so you should immediately ask, well, what is the set? And it's this nice thing. So the set is a ball centered at 0 of radius 2 times the length of W star. And, but it's a ball that is hollow. It excludes another ball. The nice thing is that the ball it excludes has C times opt, contains the vectors that all have C times opt error, where C is an absolute constant. Okay? So now what is the idea now? Well, I have a ball that excludes a ball around W star. This region that excludes a ball is actually a region in which you can show that mini-batch SGD can contract the distance to W star by a constant factor. You need additional results here, which is that roughly your variance scales as the distance to opt squared. If you have background in optimization, this is something that you would kind of immediately ask about. But what we show is that in this whole region, if you move, you're going to contract the distance. So then, the number of steps until you reach that set is going to be log 1 over epsilon. This region that is excluded has error C times opt. So what your algorithm will do, it will start at an all zeros vector. In every step, it will contract the distance until it lands inside this ball. Now, when it's inside this ball, it may not contract the distance anymore. It may even step outside. But the point is, if it steps outside, it's not going to go far. You're still going to have C times opt plus epsilon error. And as soon as you've stepped outside, you're going to go back. So maybe you'll be bouncing in and out. But after a point, all the solutions you see are going to be a constant times opt plus epsilon.
So is the variance condition the one where anti-concentration plays a role? So where does anti-concentration come in here?
Oh, it is used quite crucially in even obtaining this sharpness result. And I'm actually going to show a few lines for a very simple setup. So you'll see how it plays a role. Any other questions? Yes?
Are you going to show us what C is?
Am I going to show what C is? I'm not. But
Lambda and gamma?
it depends on lambda, gamma. For more general activations, it will also depend basically on their Lipschitz properties.
And one more question.
But polynomially on all of those.
And one more, I was just wondering about the quantification where it's universal. And I was also wondering about the anti-concentration. So are you using anti-concentration to sort of make the GELU and all of those actually look monotone? Or are you sort of...
We need this anti-concentration even for ReLU. It plays a role in essentially in ensuring that... let me actually go to just a brief analysis for ReLU, and then hopefully it will become a little bit more clear. But it is used in the sharpness result, which is the next thing. How do you even prove it? And I'm going to do just a quick proof sketch that is just for ReLU, because that's the easiest thing for me to show. And we're going to do it for an idealized or noise-free surrogate where we put ideal labels here instead of the true labels. And then correcting by true labels is just going to create like an error order opt, so you're going to get the local condition. In other words, I'm not losing that much from that. Okay? So let's get started. What we're trying to do is bound this below by the distance of these two squared. Okay, so if you explicitly write what this is, you get an expression that looks like this. Okay, now ReLU in particular is a monotone function, so you can also write this as the product of their absolute values. Okay, so now everything I have under the expectation is non-negative. So certainly if I restrict to a set, everything will still be true. My my inequality goes in the correct direction. Okay, so now I'm going to look into two possible cases where w.x is non-negative and where it is negative. I'm just splitting into these two sub-events. Okay. So if you look at the first case, both of these are now non-negative. For ReLU, this means that ReLU is exactly equal to its argument in this case. So this first term is exactly going to give you what you want, this distance squared. Okay. Now, what do we do with the second term? In the second term, this is negative, so ReLU of a negative argument is 0. But fortunately, we can use concentration to argue that there will be some non-trivial mass where we are going to have that this is greater than or equal to constant times this distance. So you get this thing squared, as you wish. And where the margin-like condition comes into play is ensuring that this part has non-trivial mass, and you can bound the whole thing below by the distance between w squared. Okay, so concentration is used once. Here, the margin-like assumption is used in the very last step. I showed you things for ReLUs. It's actually not that difficult to generalize this argument to monotone activations that for argument larger than 0 have at least some slope. For some of the non-monotone activations, you can have that some of these terms are in fact negative. So basically what the argument boils down to is ensuring that the positive part dominates the negative part. So you still get the sharpness result that we wanted. Yes?
So you're saying that, is it generically true that adversarial labels is not harder to prove stuff about with multiplicative factors than non-adversarial labels? I mean, so here you said I replace the labels by the sigma w star.
Oh, this is just for proving the sharpness result. Yeah, but there is more to the analysis. This is just the structural result that even enables us to get to those results. So yeah. Other questions? Okay, if not, I'll move on to the second part, which is about learning a neuron when we do not know the activation function. Okay, so if we go back to the setup of the problem, it looks more or less the same, except that now, instead of having been explicitly given an activation, we are given a class of activations. So now we are not only looking for the weight vector, but we are also looking for an activation in this problem from some class. Is the problem clear? We're still interested in getting constant times opt plus epsilon, still looking at mean squared error. The only thing now is that we have two things that are unknown, both this vector and the activation. Okay? So let me tell you about what was already known. If the labels are realizable, meaning that you have a function from the class that is a perfect fit, or if there is a hypothesis in the class that would have, or if the labels can fit a hypothesis from the class with the 0 mean noise, there are results that are like about 15 years old. And in this case, the problem is easier. And in fact, you can get opt plus epsilon error because the labels are not adversarial. If labels can be arbitrary, there is surprisingly little work. There is one main paper we are aware of, and it is a recent result from just last year. The paper handles a fairly general problem class. It actually applies to all, I should have said, monotone Lipschitz activations. And it only requires that the distribution of the covariates has a bounded second moment. Also takes that the labels are bounded by 1. But I think that part can be handled. The error guarantee that they get is not a constant times opt. So first, there is the diameter of the set, which often cannot be treated as a constant. It turns out that under their distributional assumptions, this is likely unavoidable, and you need some type of polynomial dependence on the diameter of the set. But more importantly, for our results, the scaling with opt is not linear. It is square root. And we are shooting for linear scaling with opt. So as far as we know, there were no prior results that get constant times opt plus epsilon, where C is an absolute constant, even if you are just looking at the Gaussian distribution and any non-trivial class of activations. Let's say anything that contains some non-trivial number of activations. That's not just one activation. OK? Yeah. I don't know, actually. It might be. As I'll show you, we actually make fairly strong distributional assumptions. So I think that perhaps under our distributional assumptions, it is possible to get, even with their techniques, linear scaling with opt. But it's basically a separate work because the techniques we use are entirely different than what was in this paper. Okay. So now we have a more difficult problem. So here we make more stringent assumptions about the distribution and class of activations. I should say we know how to relax some of these to some extent, which we did not do in the initial version of the paper because it already got really technical. The paper is 56 pages. But yeah, so our goal here was to just get this result. But they're not too bad. So in terms of the distributional assumptions, we assume what is known as LR well-behaved assumptions about the distributions. And what this says is that if you look at any two-dimensional subspace of RD, the projections of the PDF of the projections on that subspace satisfy anti-anti concentration. So here I have the specific definition of what that means. And we have this condition on the PDF, which implies both concentration and anti-concentration. So we are going back to kind of those stronger assumptions from prior work. But it is important to note here that this does include all isotropic log concave distributions. Yes?
Why is it infinity norm instead of like 2 norm? Or?
Doesn't really matter that much. You could replace it with the 2 norm, and it would be fine.
Do you have dimension factors in your C?
Dimension, no. Then I wouldn't be able to claim it's an absolute constant. It is independent of the dimension. So the constant C is only allowed to depend polynomially on L, R, and this A and B.
I'm just asking because maybe using the 2 norm would introduce a dimension.
Oh, it's possible.
Because I think in the previous anti-concentration results, there was 2 norm.
I'm sorry?
The previous ones, I think, required the anti-anti concentration only for the 2 norm, not, so this is like a stronger anti-anti concentration required.
Yeah, I'm a bit puzzled. So here L is independent of the dimension,
Yes,
and R is independent.
yes.
But then I don't understand if the volume of that box is R to the D, right? And therefore L has to be, if R is 2, the volume of the box is exponential in D, so L must be exponentially
I
small.
think this is in the projected space. X
Ah,
space.
It's in the project. Yeah, it's a two-dimensional projection.
So maybe that's why the 2 and infinity is also not.
Oh, then it
Yeah.
doesn't matter.
Okay.
But then you can take the diagonal of the box, which is why I get confused.
It's only root 2, right? Because
It's only root 2.
But the diagonal has like 2 B's.
no, no, it's
No, but it's root 2 here because it's two-dimensional projection. Oh yeah.
it's root
Thank
B
you.
when D is 2.
Okay, there is a telegraph without.
Okay, very good. There are people here who think better than me.
Summation
on this.
propagation.
Okay, good. But you can very easily argue that this will include all isotropic law concaves. I think we took infinity. It was just simpler for bounding some integrals, like you get rectangles that you bound. But yeah, glad we cleared that out. The class of activations are all AB unbounded activations. So if you exclude the last bullet, this would basically just correspond to what people usually assume for monotone and Lipschitz. We just have this additional assumption is that when the argument is non-negative, that the slope is bounded below by some A. Okay, so you capture ReLU, you capture also some other activations, you capture anything weird looking like this. Doesn't need to be invertible, by the way. Okay, any questions about that? I would say it's not too bad as a class of activations, and I'll tell you a little bit more. So when it comes to, without this last part, if you were just looking at the class of all monotone Lipschitz activations, we do not have a result that gets constant times opt plus epsilon even under these distributional assumptions and even for a known link function. Yes?
Here the non-negative doesn't matter, right? Even if it's on the other side, it would be fine. You just want some part that has some linear growth. So that you get some signal, right?
Yeah, I think so. Here it's nice to assume this because you want to capture value. Okay, so let me tell you the statement of the theorem. So here the algorithm is not SGD. It's a little bit different algorithm as you would expect. But and I'll give you also a summary of the algorithm later. But under the distributional assumptions from the last slide, for the class of activations from the last slide, we can output a hypothesis that corresponds to an activation from the class and the vector of bounded diameter. So it is proper learning, where for an absolute constant C with high probability, we get this constant times opt plus epsilon result. The total number of samples that the algorithm uses is polynomial in this diameter W, and it scales with D over epsilon squared. The runtime is polynomial in the sample size and the dimension, so it's a polynomial time algorithm. Okay. Questions about the statement of the result? Okay, good. Then in the remainder of the time, I'm just going to tell you a few words about some main ideas and what becomes different and kind of non-trivial here. And what we used as the main structural result is something called alignment sharpness, and why we call it that, it will become clear in a little bit. So the first thing we were trying to do was try to generalize the insights from this first paper to the case of an unknown link function. So the first thing we were wondering about, is there a notion of sharpness here that works? And well, you know, the kind of trivial thing is based on our prior results, yeah, the sharpness holds if you put here the target link function, but you don't know the target link function, so how on earth would you use this? Because the algorithm gets specified using this gradient. So another idea you could think about is, well, maybe if I put a different link function there, there is still some notion of sharpness that involves both these vectors and the link functions. And actually, that's not true. There are very easy examples you can construct where you can have the link function and the vector be very far from the target ones. The mean squared error is also kind of far from the goal, but these are actually negatively correlated. And we're trying to show positively correlated with something that is non-trivial. Okay, then you start looking at this a little bit more, and the next idea is, well, but I'm not interested just in any link function weight vector pair, because I know that at the solution, if I have a target vector, W star, I would be using the best fit link function, the one that minimizes the square error. So maybe we can just restrict ourselves to the pairs where the link function is the best fit function from the class for this vector with respect to the mean squared error. Okay? And this still doesn't quite work. In particular, you cannot get this. And the quickest intuitive explanation comes from just thinking about the link functions that are locally linear. Because if you scale up the vector and you scale down the, if you scale, let's say, up the link function, you scale down the vector, you get the same value of both the surrogate loss and the mean squared error. So in other words, the surrogate loss does not really carry information about the scale of the weight vectors. So the bad thing really happens when these two vectors are parallel. But it turns out that's the only thing that can go wrong. So our main structural result for this problem is that the surrogate loss does, in fact, when you look at the best fit link function for W, it carries information about the misalignment between the vector W and the target vector. That's the intuitive explanation. This is a more formal statement, which is that under our distributional assumptions, there exists an absolute constant mu, again, that will depend on that LRAB, but polynomially, such that for any weight vector from our feasible set, something like this holds. So let me tell you what this quantity is. So this is just the projection of the target vector to the orthogonal complement of W. This error is going to be dominated by this. Whenever your vector W has roughly the same scale as W star, and this is not an O of opt plus epsilon solution. So in other words, it is possible to use a result like this to contract the distance to W star, but you need the right scale. So I showed you a picture for the previous result, and I'm going to show you an illustration here for what this, if you think about this as local error bound, what the set would hold. So in the previous case, we had a ball that excluded another ball. In this case, we have a sphere with radius equal to the length of W star that excludes a spherical cap around W star. And similar to what we had before, the region that is excluded is a region with C times opt error. And you can make a similar argument if you got the right scale and you take the appropriate step sizes, you can be contracting the distance to this set. And once you land here, you're done. Okay, so I'll give you a quick summary of the algorithm. The algorithm does need initialization, but it's actually not very difficult to do initialization. All you need is that you have some initial non-trivial alignment with W star, but not too small. Just, you're not orthogonal to it. To resolve the unknown scale, we run the optimization routine for the guesses of the scale of or the guesses of the length of the target vector. The grid has width root epsilon, so there are W over root epsilon guesses. The optimization is essentially an alternating approach where you do a Riemannian gradient descent step on a sphere of radius that is one of these guesses. And then you do a best fit update for the activation, obviously on the empirical version of the loss, and that suffices. So you need to be a little bit careful how you carry out the whole argument. And then the last part is just to pick the hypothesis, which you do with standard testing. You draw another sample that is not going to be too large, and you just pick the hypothesis that has the lowest mean squared error. Questions? Yeah.
So if you do a no-opt, how do you stop the algorithm?
Oh, so the you can bound the number of iterations that are needed, but in that case, you need to know the parameters of your problem class, right?
Yeah, but you don't have any guarantee of the gradient inside that ball, right? So
it's the same argument as for the previous one. So you guarantee that at some point you're going to hit that set. You may step outside of the set, but you won't go far. You'll still have a C times opt plus epsilon solution. So if you step outside, you're going to step back in. Yeah. So it will always be the case that a certain number of steps suffices. OK. So to summarize what I talked about are results with error guarantee of opt plus epsilon for agnostic learning of a single neuron with a known or unknown activation. When we know the activations, the results I showed you apply to more general classes of distributions and activations. And they either have a matching or improved sample and computational complexity compared to the prior work. For unknown activations, the results is the first that has the error of opt plus epsilon for essentially any non-trivial class of distributions and activations. The results are based on structural results that come from, whoops, what did I accidentally click this. The structural results that come from optimization that we called sharpness and alignment sharpness. The way to think about them on an intuitive level is that if your problem is nice enough, then there is a strong signal that can point you towards the set of solutions. That's basically what these local error bounds do. And this wouldn't be a computer science style talk if there weren't open questions. These local error bound ideas are quite useful. They enabled all the results that we got. And just a broad question is, can we use them for other problems in theoretical machine learning? I should mention that ideas like this have been used in some low rank matrix problems. So there are certainly some examples, but we don't have many. Now, this is something I hinted on. But if you have only monotone and Lipschitz activations, we don't know how to handle all of those simultaneously with O of opt plus epsilon error, even if we know the activation function. This is an open problem. And finally, it would be nice to get similar results with similar techniques when going beyond a single neuron and the first example to look at would be just the sum of ReLUs. Okay, so I'll stop here, and thank you very much for listening. I'm happy to take any